All right, so we're going to be talking about scaling. And so scaling is critical because it we have these sensors and we have to get these sensors scaled to the point that they mean something. So we've already talked about the analog signals, and the idea is, you've got a analog signal is a voltage from 0 to 10 volts or a current from 0 to 20 milliamps. Well, what does that mean? How does that relate to what we're actually trying to measure? So if we look at it, these sensors are outputting these analog signals based on some sort of process parameters. So we have this term, again, in my slides, right? Anything that's been highlighted with like a different color or anything, is probably going to be, more than one test question on that. So a process parameter is also known as a process variable, is what we built the sensor to actually sense. So it could be temperature, is it hot or is it cold? What is the actual temperature in degrees Celsius or Fahrenheit? Is it a force? Okay, so load cells. One of the things we'll be doing in lab, we'll do several labs with what's called a load cell. And load cells actually measure force. And so they can, they measure force, but the interesting thing about these load cells to me is the fact that they output the signal in a range from about 0 to 45 millivolts. Now this is millivolts, right? That's 1/1000th of a volt. That's very small. And these millivolts here can, we talked about the attenuation, right? Voltage signals have a huge attenuation, especially when it starts out that it's tiny to begin with. So we'll be using converters for these. But these 0 to 45 millivolts is the output, but the weight could be 1,000 pounds. Okay. And so we want to know, well, hey, if this is a 1,000-pound load cell and I, put a elephant on it or something, what's the voltage that it's reading, but more importantly, what is the weight of this elephant? Okay, and I think full-grown elephant probably weighs more than 1,000 pounds, so we might need a bigger load cell or something. But the idea is the fact that is what we really want to know is what is the weight of this object. We don't really care how many millivolts the load cell is putting out. So we need to scale the reading into a reading telling us, how many pounds it is. All right, and the nice thing about a lot of these analog sensors is the fact that they actually output a linear value. Now, not all of them do. We'll talk about that. The upcoming lecture is going to be transducers, and we'll talk about that. But a lot of these sensors actually output a linear value, which is nice because it lends to scaling very nice. Okay. So, but the other thing that we got to keep in mind, we've been talking about these analog to digital converters, and they are simply converting them into a count. How many, a binary number inside of the PLC. And so we need to keep that in mind too when we do this scaling. So let's take a look here first. If our sensor is outputting a linear range, which, like I say, a lot of these sensors do output a linear range, then we get a nice straight line. That line has a slope. Okay, so they usually use this equation here. This is the equation of a line, a straight line, and it has what we call a slope and an intercept. Okay. If the slope is negative, then that means it's going to decrease as x gets bigger, y decreases. Okay. If it's positive, then y gets bigger as x increases. Now, to find this slope, we need 2 points. So we need to have a point over here, x2, y2, and we also need an x1, y1 point. All right, so we've got this here. This is the second point, and then we have the first point. Okay, and so what we do here is we have to find the slope. The slope is y2 minus y1 divided by x2 minus x1. That gives us the slope. So we need to take 2 points and determine both the x and the y value for each one of those points. And then we can determine the slope of this equation here. All right, once we have the slope, then we can determine the intercept. We take one of the points. So to find B, which is what we call the intercept, that is where it crosses the y-axis. Okay, so we're looking, this intercept is going to be when x is equal to 0, where is it crossing? Okay, and so B, the B term is the intercept term. We can either evaluate that with point y2, so we would take y2 minus m times x2, and that'll give us B. Or we can use the y1 point, and so we can say y1 minus m times x1. That'll also give us the exact same B. Okay, so we can use either one of these. Now, a lot of times, if we have x1, if our first point that we collected was 0, if x is equal to 0, it makes this really easy because then B is simply equal to whatever value y1 was. All right. So no, we're not always this lucky, but sometimes we are, where x1 is actually 0. So you want to, most of the time I find when you're trying to figure out B, you want to use the first point because either x1 or y1 is 0. Not all the time, but sometimes we get lucky and one of those two are 0, and the equation gets a little easier. But you can actually calculate it using either of the 2 points. But you first have to have your 2 points and calculate your M. All right, so here's an example of a load cell. Okay, and this load cell is actually a very large load cell. And so this particular load cell actually has a 75,000 pound capacity. All right, and you can see in the top right corner there is some a little data sheet talking about this load cell. All right, and so this is what they actually use for to weigh a truck. So you see like a large dump truck there in the one picture on the left up there, and we're trying to weigh, how much does this truck weigh, especially when it's fully loaded. So when they're trying to figure out how much a truck is carrying, you first got to weigh the truck with nothing in it, and then you load it up, and then you drive it back on the scale, and you can find out how much of a load was actually put in the truck. All right, so the load cell can detect up to 75,000 pounds. But again, the load cell, even though this particular load cell can handle 75,000 pounds, it's only going to output 45 millivolts. So when this load cell is at its maximum capacity of 75,000 pounds, it's going to output 45 millivolts. If the load cell is outputting 0, then that means it doesn't have any weight on it at all. It's empty. Or at least that's the theory. Now, unfortunately, sometimes when there's nothing on it, it is actually outputting a non-zero voltage. And so, so an ideal load cell with nothing on it would output 0 millivolts. But in reality, it might be outputting non-zero millivolt value. Okay. All right. So, but what we're going to do is we're going to take this load cell and we are going to run it through a signal converter. We kind of talked about those before, but we haven't really used them yet. But we're going to run it through the load cell, and it's going to the load cell, then we're going to generate a 4 to 20 milliamp, or the converter, after we go through the converter, it's going to output a 4 to 20 milliamp signal to the to our PLC then. So we'll have a 4 to 20 milliamp signal going to the PLC, and then the PLC is going to have an analog to digital input card and generate a binary number for that card. All right, so this is just kind of showing the pictures a little bit larger there. All right, so we need to determine this. If I have 20 milliamps, okay, if I have 20 milliamps going into my PLC, what is the weight on the load cell? And then what is the binary number inside of the thing? So we're going to do an example here as we go through there. But to scale that, then inside the PLC we have a compute statement, and you should have discussed these in the PLC 1 class, but you probably didn't do too much with them. But the compute statement just allows you to build up some kind of mathematical equation. All right, and so the beauty of this is we just need one compute statement. We have our input. Let me zoom in on this a little bit. So if we calculate our slope, okay, so this is just an example of a compute statement here, but we have our slope times I colon 6 is the input. Now this notation is was from a SLC 500 PLC, so we're not using tags. It's an older style PLC. So the I is our input. This is our analog input. It was in slot 6 and it's channel 0. Okay, so this is our input. We're going to multiply that times the slope, and then we're going to subtract the intercept, and we're going to store that in a floating point value. Okay, so that is our this is what the compute statement looks like. Okay, even in RS Logix 5000, the only difference is with RS Logix 5000, we can actually create tags for these, so they're not just I's and F's, but they're tag values. All right, but so we're just going to do a compute statement. Now notice over here, there's no contacts on the left side of this rung, right? This is a rung, and what does it mean when there's no contact there? Okay, one of you guys want to pitch in here and tell me? There's no contacts to the left of this, so we have a compute statement. When is it going to be executed? When I press the green start button? Yeah, exactly, Robert. Yeah, that's correct. It's going to be all the time, right? Every scan, okay? Every scan of the PLC, I'm going to execute this compute statement because it's just hardwired, all right? It's just from the power rail over here, you know, if you consider it a power rail, every single time through the scan, it's going to execute this compute and give us this weight all the time. That's all right. So here's an example with a sensor that's going to measure the weight. So I have a 1,000 gallon tank. And so I've got my sensor. And remember, typically the sensors will output a 4 to 20 milliamp kind of signal, which means when the tank is empty, I'm getting 4 milliamps, not 0 milliamps. Okay. And again, the reason we do that is because if my PLC is reading 0 milliamps, it tells me I've got a problem with my sensor, as opposed to the tank being empty. All right, so we have a non-zero feed into our PLC, even though the tank is empty, and that tells us that at least the sensor is working. All right, so when the tank is empty, that means 0 gallons. All right, we're going to output 4 milliamps. And when the tank is full, we're at 1,000 gallons. Okay, and we're going to feed that into our PLC, which is a 12-bit analog to digital converter. Okay. So the first thing we need to do is convert how many, what is the count, what is the number inside the PLC if we're getting 20 milliamps. Okay. So our analog to digital converter is going to read 0 milliamps as 0 counts. So remember, the analog to digital converter reads from 0 milliamps. The sensor is going to output 4 milliamps. If it's working correctly, it's going to output a minimum of 4 milliamps. So the sensor will never give us less than 4 milliamps if it's working correctly. But our analog to digital converter is going to be reading starting at 0 milliamps. So the question, you know, one of the questions is going to be, well, what is our count when there's nothing in the tank but the sensor's working? Okay. So how do we do that? Well, it's a 12-bit converter. So 2 to the 12 gives us 4,096. Okay. But the count range, remember, when you start counting at 0. And so when you start counting at 0, your last value is 1 less than this value. So it's actually 4095. Okay. So this over here, let me see if I can do that. This is our X1 value. This is our Y1 value. And this is our X2 value. and this is our Y2 value. And so you can see here we're doing Y2, which is 4,095 minus Y1 divided by, oh, I got that backwards right there. That should be 20 milliamps minus 0 milliamps. Okay, so yeah, so remember it's Y2 minus Y1 and X2 minus X1. All right, and so what that means is that for every milliamp, I get 204.75 counts. Okay, so every time my sensor increases by 1 milliamp, my count inside the PLC is going to go up 204.75 counts. Now, that is a little bit misleading because remember that I'm not getting the decimal point. And so it's actually, you know, if it goes up 1 milliamp, it'll actually only going to go up 204 counts. All right. But if I go up 2 milliamps, then, you know, this will round up and it'll go over. So when you do your scaling, you need to use 5 significant digits. Because remember, like in Blackboard, when you record your numbers, I want 3 digits for your answers. So your scaling, when you do your scaling, you need to keep 5 digits. Otherwise, round off will give you a wrong answer. Okay, so when we do our scaling equations, you're going to be required to have 5, your slope, carry your slope out to 5 digits, and your intercept out to 5 digits. Now, the nice thing about this intercept, because X1 and Y1 are both 0, then that means B, right? Remember that B is equal to Y1 minus M times X1. But in this case, Y1 is 0 minus M times an X1 is both 0. So B is simply 0. All right, so there, you know, this is for the analog to digital converter, but you're both, and this may not always be the case, because your Y may not be a 0, but in this case at least, that B is simply 0. So that makes it a little bit nicer. So you only have to worry about the slope. So now the question becomes, remember that our sensor is not, when the tank is empty, our sensor is going to send us 4 milliamps. And so we can now evaluate that. What is the count inside of our PLC? What number is the PLC going to tell us if this tank is empty? Well, the sensor is going to send us 4 milliamps. We multiply that times the slope, which is counts per milliamp. Now notice what happens here. The milliamps cancel. So when you do this, you always want to record the units in your equation when you're doing this, so to make sure that you get it's count per milliamp and not milliamp per count, so that the milliamps will cancel and you're left with counts. So the number inside of your The number inside of your PLC when the tank is empty and the sensor is outputting 4 milliamps is going to be 819. Okay, so when the tank is empty, you're going to have a number coming into your analog to digital converter. That number is an integer value, right? There's no decimal point here. It's an integer value. Okay, so let's take a look at this. Let me calculate this. Okay, I like to use this Octave program. It's just kind of like a overgrown calculator. So, because anytime I'm doing this, I'm at a computer. And so this is my calculator. And this is really nice because we can actually like calculate our slope. So we could come in here and, we could do our calculate our slope is going to be 4095 minus 0 divided by the 20 milliamps minus 0. And, that gives us our 204. And now when I want to calculate Y value, I can then, use this slope. So this is going to be Y is equal to M times, and then if I want 4 milliamps, I can put that in there, and that gives me 819. But what if I wanted, what about when it's 6 milliamps? Then I get this value, 12.28.5, all right? And that's the idea of this equation. We can say, well, how many gallons? At this point, this is just a count, so I still have to scale it to gallons, okay? But at this point, we have, when there's 6 milliamps, I'm going to have this number coming into my analog to digital converter. But remember, there's no decimal point, so you do not round this up. The answer is going to be 1228. Now, in the classroom, we do have this Octave program, but if you can install it. This is a free software. You can install it on your home computer if you want to use it, or there's an online version of it. If you go to the website octave-online.net, you can actually just run this right here. So I can do this like M is equal to 4095 minus 0 divided by 20 minus 0, and then Y is equal to 4 times M or whatever. So so this is just kind of like a online version of this Octave software that you can always just go to also. All right. And again, the thing I like about this, as opposed to just opening up Windows calculator, is the fact that you can create these variables, Y and M and B. I didn't use B, but I mean, if B is equal to 0. So then, and you can use your up arrow key to recall these, and you can stick in your different values. Oops, that should have been B, right? And to do these calculations. Okay, so it's just kind of a nice little software for that. All right, so when we do that, then, right, our 4 milliamps gives us 819 counts inside the PLC, okay, for 0 gallons. And at 20 milliamps, we're getting 4095 counts inside the PLC, okay, which would be 1,000 gallons. Now, this is an ideal case, okay? And so now, this, if we scale that, then we get 819 counts for 0 gallons and 4,095 counts for 1,000 gallons. Should probably be a comma there. For 1,000 gallons. And so our slope is 1,000 gallons minus 0 gallons divided by 4095 minus 819. So our slope, gallons per count. Now what we did back here, what we did here was we were doing counts to milliamps. Okay, this was counts to milliamps. But now what I'm doing is, what I really want to know is how many gallons are in my tank. Okay, I want to know how many gallons are in my tank. And so I'm actually, now that I've got my number of counts inside of the PLC, and I know how many gallons that is, right? Because what I had to do on the other slide was figure out what this counts was for 4 milliamps. That was kind of why I had to do the previous slide. But now I know that 4 milliamps means 0 gallons, and inside my PLC that's 819. And 1,000 gallons is 4,095 counts. So I can calculate a slope for gallons per count. And so I take my gallons, 1,000 gallons minus 0 gallons, and then 4,095 counts minus the 819 counts. And that gives me a new slope here with units of gallons per count. So as I said before, you've got to record, you have to record the units on this so that you know exactly what this slope is referring to. So this is actually going to tell me how many gallons are in the tank. All right, and then I have to calculate the intercept. Now in this case, I have my X or my Y value. This is my Y1 value. My Y1 value is gallons, 0 gallons, but the X1 is not 0. So I come over here, I'm going to calculate the intercept, which is Y1 minus M times X1. Okay, and Y1 is 0, so that gets rid of that one. And then it's just minus the slope that I calculated up there times my X1 value of 819, which turns out to be, to 5 significant digits, 250.00, 250 gallons. Okay, the units of this is simply gallons, because we have gallons per count times 819 counts. So I did not put the units on here because I was kind of running out of space, but the the units of this intercept match what you're looking for. So like notice I'm looking for gallons, so the B, the intercept value, is just gallons. The slope is gallons per count, and X is in counts. Okay. Remember, a count is like one more value added in that binary number inside of the analog to digital converter. So, every time you go up, every time the number goes up 1, you went up 0.3 gallons. Okay, so every time your count goes up 1, you're going up 0.30525 gallons. So if the count is 0, we have minus 250 gallons. Okay, because remember, if the count is 819, if the count is 819, then that means we're outputting 4 milliamps, which means that we're at 0 gallons. So what you get all the time, if you have a 4 to 20 milliamp sensor and you're scaling it to get it back into actually what that sensor is telling you, how many gallons are in the tank or how pounds the load cell is or whatever, when you're scaling that back, you're going to have a negative here. You're always going to have a subtraction because you're basically trying to take away this positive 4 milliamps that the sensor is outputting when there's the sensor's reading a 0 value. Okay, so that's why this is negative here, because our sensor is giving us a positive 4 milliamps when we're at 0, and so we have to subtract that off of there, and that's why this is a negative. So when you're looking for what the sensor is actually telling you, how many gallons are in the tank, but if there's no gallons in the tank and the sensor is giving you a positive 4 milliamps, you're going to, or whatever, you're going to have a negative intercept. All right, now again, I marked this as being uncalibrated. This was assuming that the sensor was reading exactly 0 gallons when it output 4 milliamps, and exactly 1,000 gallons when it's reading 20 milliamps. In reality, sensors are almost never perfectly reading those values. So what we actually have to do is we have to measure we have to kind of, know exactly how many gallons are in the tank and measure the current. And then we have to, put in, some more water or whatever goes in the tank, but we got to know exactly how much we put in and read the sensor again so we can get 2 points. Remember, we always need 2 points. And so we have to kind of start with the tank empty. Now, a lot of times the problem with the sensor is when the tank is empty, the sensor isn't actually able to detect it. So the sensor may not even detect anything in it until you got 50 gallons in it. So you've got to get it up to the point that the sensor is actually detecting. All right, and then you have to know how many gallons are in it, and then you add 600 gallons, and then you read the new value of the sensor, so you get at least 2 values, and then you can come up with your scaling equation. All right, so you actually have to test it with known values, know how many gallons are in it, and then put more in it and then test it again, kind of deal. But you've got to know you have to know how many gallons you added and then read the value that the sensor's outputting. All right, so when we calibrate this, so here's the same example, only we calibrated it. And so what we found was that after we put 42.3 gallons in the tank, and we got a reading of 4.05 milliamps. Okay, so again, it was like we weren't really the thing wasn't really sensing or changing or anything until we got to 42. We put in 42.3 gallons, and we were able to get some kind of change in our sensor. So with these 42.3 gallons, we got 4.05 milliamps out. Then we filled the tank up almost to the top, and we got it up to 973.5 gallons, and our sensor was reading 19.7. So now we have our 2 values. This is our X2, Y2, and we have our X1, Y1. And so we can then, again, take and determine what our counts are. So we have 829 counts when there's 42 gallons in a tank. And we have 4,033 counts when it's up to that 973.5 gallons. So we can then calculate our slope, which is the big number of gallons minus the little number of gallons, and then the big number of counts minus the little number of counts, and that gives us 0.29064 gallons per count. Okay. Now again, when you do this, I want to see 5 digits. Okay. I want to see 5 digits for your slope and for your intercept. So then I calculated the intercept using y1 minus m times x1. So y1 was 42.3 gallons. Then we subtract off our slope times our count. And so again, I need 5 digits here. All right, and so my intercept is minus 198.64 gallons. Okay, so remember on the uncalibrated one, it was 250 gallons exactly, even, right? I mean, that actually came out perfect to 250 gallons to 5 decimal places. But remember, before our sensor even started sensing, we actually had to put almost 50 gallons in the tank. It turned out to be we had to put in 42 gallons. So that's why you see there's this instead of being minus 250, it's about minus 200, right? Because we didn't even start detecting it till we were close to 50 gallons in the tank. All right, so this then is our scaling equation. Okay, our number of gallons is equal to 0.2964 gallons per count. So when we read in that count into our PLC, and then we also have to subtract off then this. Again, we're subtracting this off because when the tank is pretty much empty, we're getting a positive 4 milliamps into it. So that is a calibrating, that is calibrating the sensor. All right. For the compact logic PLCs, and I did a video of that, or I'm working on a video of that at least on these two. I'll try to get that uploaded later today. But the compact logics, as I say, they do not give you a floating point value. It's an integer value. All right. But they actually give you a 16-bit value. It's a 14-bit. The analog to digital card in the compact logics is actually a 14-bit converter. But what they do is they basically ignore the last 2 least significant bits. And so what you end up getting is values that go from positive 32,767 to a negative 32,768, which is kind of weird. Or you can set it in what they call engineering units, which is actually microamps. So if you're sending it a 4 to 20 milliamp signal, what they do, because it's an integer, you can't have a floating point. So you couldn't have something like 4.5 milliamps. So what they do is they multiply it by 1,000, so it's actually going to read microamps. Okay. And so you can set those values in there. Okay. But again, like if we come back here, if this was my equation, then I would do my compute statement. I would have my compute statement inside the ladder logic. Inside that, I would do a compute statement there of, you know, I would have like my output tag, which I would create a tag called gallons or something. Gallons in tank. Okay. Create a tag kind of like that. And so that would be my destination of the compute statement. And then the actual compute we would be my 0.29064 times, and then this would be my input channel 0 from my analog input minus the 198.64. So this is what I would put in for my compute statement. So if I go back here, all right, this is what that rung would look like. So you would have that slope times that input, and then you would be subtracting off your intercept. Okay, so we use that compute statement. Compute statements are, where's that? CPT. CPT stands for compute, and it's just a mathematical expression. So you can multiply, you can add, subtract, all in this one expression. And then the destination is going to be the tag where you're going to store that result. And that result for that would then be gallons for this example here, right? Because this is how many gallons are in this tank. All right, so that's it in a nutshell, I guess, for the scaling. Is there any questions? Okay. All right. Well, I guess, like I say, that's pretty much it. So if you guys don't have any questions, if you do have questions, remember, just shoot me an email and contact me. And, if you want to, we can always log into Blackboard here like this and do a one-on-one session or something, or what. But there'll be, I think there's already the homework set up in Blackboard. If not, I'll be putting it out there. And there's also the lab. Okay, when we do the lab, we're gonna use the compact logics for the next lab, and some of the exercises we're gonna kind of do these readings, and then you have to do some scaling for that. So. But yeah, but we use the control logics. Now we're going to use the compact logics and see that a lot of it's the same, but there's a couple of little differences. One of the big differences is they don't do that floating point conversion in the configuration, so you have to do it in the ladder logic. So.